Hi viewers, welcome to all. Here we are discussing about a project hardware architecture for adaptive edge directed interpolations algorithm. Okay, the term demosaicking refers to the process of recreating a full color image using only partial color samples that were obtained by a single chip image sensor. Therefore, the interpolation is required in order to acquire the missing color pixel. An adaptive edge directed interpolations method that employs an edge estimator for the interpolation has been proposed in this study, along with a hardware architectures for this algorithm's implementations. Okay, here we may be able to improve the image resolutions on both sides if we give a green the highest priority throughput than the color interpolation process and make use of a strategy that involves the pooling hardware resources. In order to accommodate the hardware sharing strategies of red, green and blue interpolations, the arithmetic operations will need more logic sizes and the VLSI designs will require the higher gate count. Okay, a color demosaicking approach that makes use of carrier skip adders as opposed to a normal ripple carry adder would be included into all existing ways for hardware sharing as part of the project. Okay, so this would allow for the reductions in the amount of area, times and energy that would be required. The experiments are carried out as a part of this study, making use of the VHDL programming language and synthesized capabilities of Xilinx Spartan 6 LX 150 FPGA at using a clock frequency 200 MHz in order to develop the color demosaicking method using 256x256 image resolutions. Okay, now we can verify the base paper. This base paper is purely designed for the image demosaicking method, okay, with the adaptive edge directed interpolations algorithms. Okay, so here the image demosaicking algorithms we have used some reference with supporting of this paper. Okay, so fully pipeline, low cost and high quality color demosaicking VLSI designed for real-time video application. Okay, the same method will be covered up with this paper also. Okay, but here this is a publication 2015. Okay, but that paper is a recent publications. Okay, so here they are handled the hardware sharing machines 1 2 register bank 1 2, okay, and boundary mirror machines, the control unit. Okay, and they are given number of hardware machines. Okay, so as per this papers, the updations of this work, okay, we have developed this work. Okay, that is a adaptive edge directed interpolations algorithm. Okay, so here they are given the main architectures in figure 3, the proposed VLSI architectures for adaptive edge directed interpolations algorithm. Okay, so here also they are handled with the number of block as per the hardware sharing machines. Okay, but the name will be differ. Okay, controller, register bank and G interpolator, memory, GB interpolator, RB interpolator, layer 1, layer 2. Okay, but what is the main difference means here they are splitted the images up to the 5x5 matrix sizes. Okay, so initially we are used as a line buffer as per the figure 4 architecture and construct a 5x5 image sizes from 256x256 image resolution. Okay, so with the help of this line buffer. Okay, and the balance architectures, the candidate interpolations shown in figure 5, horizontal edge detector shown in figure 6 and green channel interpolation shown in figure 8 and bias gradient shown in figure 9. So here we are developed all the architectures, okay, with a two different level of comparisons. One is a ripple carry adder and another one is a carry skip adder based comparisons. Okay, so why we are choose the carry skip adder means here the carry skip adders will reduce the power consumptions and delay consumptions and logic sizes compared to the normal adders. Okay, that's why we choose this carry skip additions. Okay, so we have choose this architectures, the shown in proposed CICSK architectures will be designed addition part of this models. Okay, so here vertical edge detectors means it's having a adder unit, right? So that adder unit will be replaced with the carry skip adder. Okay, so here the balance architecture is a figure 10 diagonal gradient and figure 11 anti diagonal gradient and red channel interpolations in green channel. Okay, so here Yeah, figure 12 shows a red or blue green channel interpolations, and figure 15 shows horizontal and vertical gradient of green channel interpolations. Okay, so here all the blocks they are given, but the each blocks having a interconnections between them. Okay, so here R34 means dv bgm, sorry, beta gm and bg and gp. Okay, this signals will be developed from here. Okay, so here, okay, and GHG dv gv dh means it will be generated from here. So here all the blocks will be interconnected, and once we develop this all the block, then only we will come up with the top model perfectly. Okay, so now we can go through the Verilog HDL coding and the top model of architectures in the RL schematic. Okay, so here this architectures developed in Verilog HDL. Okay, so the Verilog HDL start initially with the support of MATLAB GUI. So once we load an input image to the MATLAB GUI, and it will be converted into the hexadecimal file, and that hexadecimal file will be loaded into the memory. Okay, after that we are reading the memory, okay, with using a top model. Okay, here we are used as a file reading code, memory block coding, and file writing code. Okay, and this is a top model code. Okay, so AED interpolations algorithms. Okay, adaptive edge directed interpolations algorithm. Okay, this is a top model. So instead of this top model, we have used as a image line buffer. Okay, so initially the input image we need to convert into the 5x5 matrix. Okay, so 5x5 images. Okay, after that we process that. Okay, so that 5x5 images means it will be splitted. Okay, so here in the figure 2 interpolations of color channels, okay, here they are given, right, R01, G02, R03. okay, as per that same way. So we are splitted the images in 5x5, then only we can give the value into here. Okay, G22, G24, R21, R25, R23, R03, R43 means it's a pixel value. That value we are generated from the 5x5. okay, so it will be come up with the image line buffer initially start with here, and the decoding part of the image line buffer will given here. Okay, 5x5. so in between the interpolations algorithms will be used. Okay, so this interpolations algorithm will have a register banks. Okay, initially start with register banks. Okay, as per the architecture in figure 3. okay, register bank. So why it will be required means it will be splitted the images as a 5x5 pixel 0, 1 to 4, 5. okay, so here this is a first row, okay, second row and third row and fourth row and fifth row. okay, so 0, 1, 2, so 4, 5. okay, so this pixels only we are given as an input to the other model. okay, so G candidate, horizontal edge detectors, vertical edge detectors, green channel interpolation, red channel interpolation, bias gradient, diagonal anti-diagonal gradient, and RB gradient, horizontal vertical green second layer, okay, diagonal anti-diagonal second layer, green channel interpolation second layer, red channel interpolation second layer, row column index. okay, so all the blocks will be interconnected, will be here. okay, so here the proposed coding is designed with the carrier skip adder. So okay, so here you can check the carrier skip adder 8-bit and carrier skip adder 16-bit coding would be designed, and it will be integrated into the any other block. okay, so here the CSA 8-bit will be used. okay, so this is the only difference between the existing and proposed. okay, and the simulation results of existing will be shown here. okay, so this is a simulation result. So initially here this is a reading time, okay, and this is a operational mode of time, okay, for Demosaicking algorithm, and this is a file writing time. okay, so here the AED will read the data, and it will be splitted into the interpolations algorithm. okay, so here the pixel 0, 1, 2, 4, 5 will be loaded here. okay, so and it will be splitted into green channel interpolation, red channel interpolations, RB interpolation, green channel interpolation SL, red channel interpolation SL. okay, this output we are taken finally, and it will be loaded again into the row column index. okay, so here, okay, so this is a block of row column index. okay, and finally we'll get taken output from the output pixels data 1 to data 5. Okay, that output will be loaded into the memory, and finally we are taken as a output. Okay, so this is a sample reference image output. Okay, so for existing, and this is a second one. Okay, this is a proposed one of comparisons. Okay, so here we are taken number of images. Okay, and before that we need to see the synthesized report. Okay, so here this is a existing part of the synthesized report. Here we can check number of sliced registers, number of LUTs, and number of occupied slices, IO base. Okay, everything we are compared. Okay, and synthesized report we can check delay. So here the existing part delay will take okay, 28.673 nanoseconds. Okay, and this is a proposed synthesis report. Okay, here you can check number of sliced registers, LUTs, and occupied slices, IO base. Okay, and synthesis part you can check delay. Okay, delay will take 13.473 nanosecond. Okay, so here you can check the RTL schematic in the proposed method. Okay, so here the initial data read data came from here. Okay, so it will be loaded into the image line buffer 5x5. Okay, so this image line buffer data will loaded into the interpolation algorithms. After that it will be loaded into the image line buffer decoder 5x5. so this is a top model of this paper. Okay, so here you can check all the blocks will be available. Okay, register bank encoder and G candidate interpolations, diagonal, anti-diagonal SL, bias gradient, red channel interpolations, and red channel interpolations, SL, and normal. Okay, RB interpolations. Okay, everything occur, and all the outputs given into final with the row column index. The row column index will provide the data to the image line buffer decoder. Okay, so here every interpolations algorithm we have used as a carry skip adder architectures. Okay, so this is a carry skip adder method. Okay, so here you can check it. The next thing is a comparisons. Okay, this comparisons document we are updated in the table. Okay, so existing RCA with proposed CSKA carry skip address. Okay, you can check the number of parameters, slice registers, LUTs. Okay, so you can check the delays and slice LUTs. Okay, and power consumptions. Okay, and the image PSNR comparisons will be given here. Okay, so here you can check the number of images. So we have more number of images in the folders. Okay, we can possible to check the more comparisons, means we can check it. Okay, so and the documentations will be written. Okay, for this project. Okay, so title, base paper abstract, improvement of the project, proposed title, proposed abstract, existing system. Okay, so disadvantages, proposed systems, advantages, and literature survey, finally references. Okay. Okay, thank you.
If you need more video related to VLSI project, please like and subscribe this channel.